So good evening to one and all. Hearty warm welcome to day 2 session. ACT sponsored 2-week ATAL FDP on issues in satellite image processing. So this is the topic for today's session. So let me introduce today's speaker, Professor Krishna Mohan Buddhiraju. Professor B. Krishna Mohan received his PhD degree in electrical engineering from IIT Bombay in 1991, specializing in the area of digital image processing and analysis. He is a professor in the Center of Studies in Resource Engineering, IIT Bombay, and he was an institute chair professor for 2016 to 2019. And now, so Mohan sir's research interest are machine learning algorithms, segmentation and classification of high resolution satellite imagery, geospatial technologies, educational content, design and development for GIS and image processing. SAR has having 150 journals, publishings, book chapters and conference proceedings. And SAR is having 30 plus sponsored projects and 15 consultancies. And SAR taught several courses at IIT Mumbai covering areas such as image processing, machine learning and geographic information system. He supervised over 60 students for their MTech and PhD thesis. He is recognized for his work by way of holding associate editorship in journals, member of board studies in universities, referee of national and international PhD thesis, reviewer of papers submitted to over a dozen referred journals, and he is an invited speaker in conferences, workshops, training programs across the country. He organized several training programs for in-service members of the academic community. Professor Krishna Mohan sir is the recipient of IETE's MN Saha Memorial Award for the Best Application Oriented Paper published in IET Journal of Research, September 2000, and the Indian Society of Remote Sensing National Geospatial Award for Excellence in 2012. So I request Professor Krishna Mohan Buddhiraju sir, please take over the session.
Thank you very much, Dr. Rasul. Am I audible to all clearly?
Yes, sir. Yes, sir.
Yes, sir. Yes,
okay. Sir. Thank you. And thank you very much, Professor Narsimul Garu, for inviting me to deliver this talk in your faculty development program. I've been working in the area of satellite image processing for many years now, starting with image restoration and various other processing methods, then image analysis, and more recently different types of machine learning techniques. So I'm assuming that much of the audience today are not really familiar with the issues as far as satellite imagery are concerned, and therefore I'm going to introduce this from the beginning. Right, so whenever we work with images, we need to understand how the images are acquired, what the underlying principles are, and what the colors and shades in the images mean before we can deploy algorithms for useful and meaningful information extraction. Okay, therefore, I'll start with the basic underlying principles, how to actually understand what the images acquired from satellite-based imaging systems, what they convey, and then of course some of the enhancement techniques, filtering filtering techniques, classification techniques, they are somewhat common across different domains. Then again, there will be certain things which will be specific to satellite images. Okay, so this is how I would proceed in the 2 hours of time allotted to me.
Recording in progress.
Okay. Now, when we look at working with images in different domains, we have images coming from biometrics, medicine, plus natural outdoor photography, images acquired from satellites, aircraft, and drones. Okay, and also very specialized kind of images acquired by systems covering the stars and galaxies. If you have seen Hubble telescope images, and then you have images acquired, say, by very, very high resolution microscopes when you want to look at the internal structures of, say, integrated circuit devices, etc. Okay, so images come from a very wide variety of sources. I can say image processing itself had a big boost. Digital image processing particularly had a big boost during the competition or race between the erstwhile Soviet Union and the United States to put a man on the moon. So initially, the unmanned rockets with photographic film-based cameras mounted on them were sent to orbit the moon, take enough photographs, and when the rocket was coming back, before it got burnt up during re-entry, the film capsule was ejected, and it was ejected at such a time that it fell in the ocean, Atlantic Ocean or Pacific Ocean, I'm not very sure now. But waiting ships would retrieve that capsule, and then it was taken to Jet Propulsion Laboratory, which is on the campus of California Institute of Technology. And there the film rolls were first scanned and digitized. This is all 1960s. So the equipment they had was way ahead of time. So the film rolls were scanned, digitized, and using those images, all calculations, interpretations, etc. were made to identify spot where the Apollo rocket taking the astronauts like Neil Armstrong, where they could actually land. The surface should be hard enough so that the satellite the rocket would not sink. It should also be flat so that the rocket would not tilt to a side and fall. So all these calculations were made solely from the images or from the photographs collected and digitally processed, analyzed, and interpreted. So digital image processing actually got its first thrust, major thrust, from remote sensing, study of lunar planets. Of course, during the Second World War itself, aircraft-based photographs were taken of enemy territories by both the Allies and Axis forces, but mostly they were visually interpreted. Using manual equipment, all calculations were made. Here, this was digital image processing. When the attempts were made, first attempts were made to identify the location where the Apollo rocket could land on the moon surface. Okay, so digital image processing has an extremely, what shall we say, celebrated history, right? So images from space, as far as Earth observation is concerned today, images from space are one of the most widely used data sets, because these images are available from a very long time. The first civilian satellite for Earth observation was launched as long ago as 1972. So 50 years have passed since the first satellite, the Landsat-1, was launched by the Americans. So when we have these images, the processing and analysis leads to information extraction, and the information is, is driving the applications. Okay, so clear understanding of the data leads to building suitable learning algorithms. So today, most of the work is done using computers, so we can say machine learning algorithms, even though at least half of the time the images are interpreted visually by human expert just to identify quickly any changes, any anything that is worth looking at, particularly from defense point of view. Okay, but most are, for example, in disasters, like where are the building collapses, where are the floods, where are the landslide spots, etc. Okay, but all serious development applications, for example, and even applications that don't require instantaneous results, they're all now based on machine learning algorithms in the digital framework. The mechanism for image acquisition, particularly from satellites, is remote sensing. Okay, when we say satellites, it is particularly important because there are free data sets of the entire globe acquired by imaging cameras mounted on satellites. Okay, so if someone has not heard of Sentinel satellites, one of the imaging systems is based on imaging cameras operating in the visible and infrared wavelength channels. And a second satellite is based on microwave radar. Okay, so the Sentinel series of satellites provide free data of the globe, okay, in a regular mode. So you can visit the websites of Sentinel satellites and download data of whichever part of the world you want. Okay, so there are multiple coverages now of different areas, so you can even do some time series analysis. So today I'm going to briefly talk about satellite remote sensing and the imagery, the issues in processing and analysis, and some classification algorithms. Since the underlying principle of acquiring these images is remote sensing, let us formally say what is remote sensing. It's the art and science of making measurements and observations about the objects of interest and the environment with no physical contact between the sensor and the target of interest. Okay, so it's both an art and science because identifying the right kind of sensors for a given application sometimes requires a lot of expertise. Okay, and once the data is actually collected, now you should be able to make qualitative as well as quantitative observations as well as quantitative measurements about whatever we are interested in. Our forests, natural forests, our croplands, our water bodies, our mountains, our deserts, our cities, towns and villages, whatever are of interest to us, we should be able to study them. The important thing is that the sensor is hundreds of kilometers up above the earth. From there, it is collecting the reflected energy from the ground, from the earth's surface, and using the same principles, similar principles that we have for our digital cameras. Light energy is converted to electrical signals. Electrical signals are converted to digital form through A to D converters. And then the digital data is downlinked to some ground stations. Okay. Throughout the world, there are ground stations. And for every satellite, there will be certain identified ground stations which can receive the data. And after suitable processing, they are disseminated to the user community. Examples, you have some commercial satellites. Mode of operation is commercial, this Worldview series. And then Indian Space Research Organization has a series of satellites called Cartosat. The Canadians have RadarSat 1 and 2. The French people have several satellites. Okay, SPOT is actually an acronym, SPOT. Its expansion is French, so difficult to remember. European Space Agency provides the Sentinel series. The Japanese had ALOS, that is Advanced Land Observation Systems, ALOS 1, 2, etc. So these are remote sensors which provide data in the form of images. And then there are non-imaging types also. Altimeter, so it provides you the distance between the sensor and the target. Scatterometer, so based on the dielectric constant of the target, how the microwave pulse is scattered. Instruments measure the backscattered signal, and with the help of that, the terrain properties are studied, they are computed. LiDAR, so laser-based systems are used for very precise topography mapping, like centimeter level accuracy, maybe 10 centimeter level accuracy of elevation across towns, cities, and maybe coastal areas. So if you look at the electromagnetic spectrum, what we can see is very, very very, very narrow compared to the total available spectrum for remote sensing. The Earth observation is carried out in the beyond the visible region in the infrared and microwave portions of the electromagnetic spectrum. So what is measured? Measured, it is the reflected energy, that is sunlight when it is incident on the ground. Whatever is reflected is picked up by the sensors within a certain narrow angular region, because the reflected energy goes in many directions. A small portion of it reaches the sensors on board the satellites. So in a sense, the calculation is that what is the reflectance? How much is the incident light on the target of interest? How much is reflected? So the ratio is called the reflectance. The reflectance is a function of the wavelength of observation, and also the angle of the solid cone. Okay. So whatever energy is received, so with that, the reflectance properties of the terrain are estimated, and with that, using these reflectance measurements, the characteristics of the terrain materials or objects on the Earth's surface, they are studied. Okay, so the reflectance can be as low as almost 0. It will never be 100%, but it can be high depending on what kind of objects and what kind of wavelengths. And so this reflectance is highly wavelength dependent. So the basic premise of remote sensing is that each object on the Earth's surface, whether it is water, vegetation, soil, paved and built areas, snow-covered areas, sand dunes, lake and river waters, coastal sea waters, and deep ocean waters. So there will be reflectance patterns, okay, which are function of the wavelength of observation. And so if you are able to collect the received energy using sufficient number of sensors operating in different wavelength bands, you may be able to build a kind of a signature for each kind of object, and with the help of that signature, we can identify what is what on the ground. So this is a typical example of the reflectance pattern of healthy green vegetation. So in the visible region, if we see, obviously green vegetation will reflect very, very little very little energy in the blue wavelength or in the red. It reflects much more in green, but beyond green, in the infrared part, a lot of energy is reflected. And then you have, based on the chemical composition, based on the moisture content, there will be absorption in some of the other wavelengths. Okay, somewhere here, somewhere here. Okay, so this kind of pattern of low to high reflectance and then a high absorption. So this kind of pattern is unique to healthy green vegetation. Anybody who sees this kind of a pattern can readily say that this is coming from green vegetation. The x-axis is the wavelength, y-axis is the amount of reflectance. Now, vegetation is one kind. What about dry soil or water? Unless they are sufficiently different, using your sensors up in space, you won't be able to distinguish between them. But fortunately, as we see in different wavelengths, the amount of energy reflected is quite different. So this enables the practitioners of remote sensing, earth observation, foresters, agriculturists, urban and rural planners, they could use the images acquired by remote sensors and put them to useful applications. Now, there is an atmosphere between the Earth and the space, and the atmosphere is not a homogeneous medium. It does interfere with the radiation passing through it. So there will be scattering, there will be absorption, and these scattering and absorption actions, you can say, or the patterns, they are again function of wavelength. So if you see here, the x-axis shows the wavelength and the y-axis shows the transmission through atmosphere. So you should choose those wavelengths where the atmosphere allows the radiation to pass through so that it reaches the satellite sensors and images can be formed there. If you choose some of these wavelengths, the transmission is nearly nil. Okay, so these are good for atmosphere studies. Low transmission bands are good for atmosphere studies, and high transmission bands, wavelength bands, are good for Earth observation. Today, of course, Earth is only one of the planets. Mars, Moon, and some of the other planets are also being studied. Okay. So types of sensors, they operate in the optical region. So same wavelengths that our eye can sense, infrared, but very close to the optical region, just after optical. Then we have slightly longer wavelength, shortwave infrared, and further temperature sensitive thermal infrared, and then you have microwave, very large wavelength. So in optical to thermal, we treat electromagnetic, the radiation as particles, but in microwave region, energy travels as waves. The optical infrared sensors, in some sense here particularly, if you are familiar, I mean, you should be familiar with the operation of the desktop scanner that we use for documents. So there is an array of these detectors. Okay, they pass from one side to the other, and whatever light is available, that is collected, and based on that, one row of the image is formed, and the motion of the scanner gives you the other dimension. The same way here, you have a lot of sensor elements. So they cover the width of the area that is being captured in the image, and the motion of the satellite gives you the other dimension. You can say this is the width dimension, and this will be the length dimension. Length dimension is infinitely long. So if you want to purchase images or if you want to download images, you specify the area of interest, and the software will cut it and give you only the part that you are interested in. Like any other equipment or data, remote sensing data also have specifications. So what is the resolution of the data. How fine an area on the ground can be seen by the sensor elements. Okay. So the world's best today is 25 centimeters by 25 centimeters by Indian satellite Cartosat 3, I think 3E probably. 30 centimeters by 30 centimeters by American Worldview and probably one other satellite, but Worldview 3 definitely has it. So the finer the area that the sensor can view, can capture, that much will be the ability of the sensor to resolve between very closely spaced objects. So that is actually the physics definition of resolution, the ability of this ability to resolve between closely spaced objects. So very, very narrow footpaths, very small huts, onwards up to extremely large industrial, commercial, residential buildings, inner roads, highways, expressways. All these things can be captured if the sensors have high resolution or they have the ability to focus on, zoom in on very small areas. And is also useful for in defense applications to accurately recognize the kind of planes, the kind of vehicles that are being, brought in across the border, close to the border areas. And spatial resolution is like if you have a fixed geographic area, in how many pixels is that area captured? Okay, so the related number is, it relates to the spatial resolution of the sensor. So similar thing is like we talk about megapixel cameras in our mobile phones. The area of view is fixed, but in how many million pixels is it captured? So we can, when we take pictures, even very, very tiny features can be captured with cameras having more megapixels. Now, spectral resolution is like in how many different wavelength bands can the sensors collect the images. So we are familiar with only 3 wavelength bands, blue, green, and red. So within blue, within green, within red, and in the infrared region, suppose we have sensors with small bandwidth, but many sensors, each with the small bandwidth. If they collect this data, we can then distinguish between the subtle absorption reflectance patterns of the objects of interest as a function of wavelength. How many bits per pixel? So when the data is collected, in how many bits is it represented? So some of the satellites have 16 bits per pixel per wavelength, or 11 bits per wavelength band per pixel. So that is a kind of radiometric resolution, in the sense the reflected energy is captured in many distinct quantization levels. Temporal resolution, whatever area of interest you have, how frequently can the satellites provide you with images of that area? There was a time when only one satellite used to operate, and it used to take 36 days. So every 36 days you had an image. Then when other satellites were also launched by other countries, then maybe one day one country's satellite, another day another country's satellite, but you had frequent coverages of your areas of interest. Very high spatial resolution. Here it is 2 feet by 2 feet per pixel on the ground. This is approximately 6 meters by 6 meters per pixel on the ground. So this is Mumbai city. This is a very small area in Powai, Mumbai. So this is a road that runs outside IIT. And so this is an area which is largely open once upon a time. Now if you see this now, it will be full of buildings. This is 6 meters. This is 23 meters. So the area captured in the image will be really large, but the amount of detail you get diminishes. Here, small area, but lot of detail. Resolution is less, but area covered is more. Resolution is even less, area is covered quite a lot. So depending on what application you are using the images for, you can choose. This kind of data is today freely available. This will be available for a small cost. This will be expensive. When I was talking of spectral resolution, I was mentioning that if you had these sensors, each operating in a narrow wavelength band, here you can see these circles are like, each one is the bandwidth of one sensor element. So with the help of approximately 250 sensors, each operating in about 10 nanometers bandwidth, the entire reflectance spectrum of green vegetation is captured as if it is a continuous curve. So the points are so close that you can see them like a continuous signature. So one of the areas of remote sensing that deals with this kind of high spectral resolution is called hyperspectral remote sensing. So each 10 nanometer wavelength provides you one image of the same area on the ground. So if you take any one pixel and see its values in all the wavelengths, then you can plot it like a curve like this. I'm going to share this presentation with you. So some of the e-resources for you, you can use this fairly useful books and application case studies. So what do we do in digital image processing? Image acquisition in digital mode, correcting the images for distortions. Okay. Actually, these two can be combined into one. Here, I meant improving the contrast or smoothing, sharpening the images, etc. Then segmentation. So break it into edge, extract the edges, extract the regions, extract textured areas, etc. And then perform classification. And this can lead to interpretation of the image content. So in the atmosphere, we have very, very tiny gas molecules. which are much smaller than the wavelength of the radiation. And then you have smoke and dust. Here the particle size is comparable to the wavelength of the radiation. And then you have water vapor, where the water droplets are extremely large compared to the radiation wavelength in which the radiation is passing. So you have absorption here due to water vapor. You have scattering. Only very small wavelength radiation gets scattered by this, and larger wavelengths are also scattered by smoke particles and dust particles. And in this region, it's more of an absorption. Okay, so there are techniques for correcting the images for atmospheric distortions. So the distortions are in the form of collected values, recorded pixel values. So this kind of an image, after correction, it becomes a lot more homogeneous, you can see. This is a corrected image. And when you are interested in displaying the image and first looking at what it contains, you want the contrast to be improved. So there are a number of contrast enhancement methods: linear technique, histogram equalization. I'm not going into these details because I assume either these things will be separately covered or you already know them. So I'm not going to discuss these small things. Thresholding, like convert the image into a two-level image after some processing. Okay, so only the boundaries are extracted, rest of the image is gone. Now, when people view the images, what do they actually look at? Okay, this is like based on the human working of the human vision. Many computer vision algorithms are built somewhat mimicking the behavior of the human visual system. Okay, so what do the interpreters actually use? They use the color, if it is color pictures, whatever is displayed on the screen, okay? The color or the tones, the textures, the shadows, the patterns, the associations, and size, okay? I'll show you a few examples for these. Color or tone, okay? So based on these colors or the brightness levels, you can actually talk about what is what. Okay. So water bodies, human settlements, different types of vegetation. Okay, so here the color or the tone is used for identifying what is what in the image. Then the texture. So the texture is how, or smoothness or roughness, you can say. Here this can be used to distinguish between different types of vegetation. Here the sand dunes, for example, they sometimes have sinusoidal patterns, or the fault lines, the drainage channels in the hilly areas, in the mountainous areas. So they displays different kinds of repetitive patterns which are used by interpreters. So small objects versus large objects, their orientations, the geometry, they can be captured by high resolution. Okay. And then association. So here is an example of pulp mill with circular tanks nearby to hold the liquids. I'm not exactly aware of all the details, but you can see the mill areas and the holding tanks. Okay, so we can adjust the brightness, contrast, etc. by looking at the pixel values in different wavelength bands. And then we also perform slightly more involved, we can process the images in slightly more involved ways by looking at neighborhoods of pixels. So sometimes the sensor malfunctioning can give you random noisy pixels like this. So if you look at the pixel and the values of the neighbors, you can identify if there are any odd ones out. Similarly, you can also see if part of a neighborhood takes values in one region and one range versus the rest of the pixels in the neighborhood, but in a very different range of numbers. So you can see there is a vertical discontinuity, 6 numbers in the range of 60s to 178, 80, etc. Similarly here, there is a horizontal boundary here. The intensity gradient is vertical, so top to bottom there is a sharp change, and this leads to a horizontal boundary. Similarly here, in the horizontal direction there is a steep gradient, so that leads to a vertical boundary. Similarly here, diagonal. What kind of neighborhood operations? So if you are familiar with convolution, many of these operations can be performed as convolutions. So the image F convolved with a filter denoted by H. So the filter size is actually the size of the neighborhood that we are considering. So we can, smoothen the image so that the image areas in the image look more homogeneous. The sharpness slightly reduces. Okay. Sometimes if you have noise spots here and there, you can then remove them through neighborhood-based operations. And then convolution doesn't apply when the filter coefficients vary from one position in the image to another. So this is particularly useful to preserve the boundaries. So here, the smoothing can happen across land and water. But if you want the water pixels to be separately treated and the land pixels to be separately treated, then you should have these convolution, have these filters which are not based on convolution, but the filter coefficients vary from one position of the image to another position. In that case, the boundary sharpness can be better preserved, and the smoothing happens within homogeneous areas, not across the boundary. So boundary sharpness is better preserved. You can see an adaptive filter here. This is the input image. This is with the different levels of smoothing, and with suitable modifications, this filter, by tweaking some parameters, it can also be used for sharpening. Okay, so this is the input image. You can see these images are looking sharp. So the building boundaries, tree crowns, they're all very, very crisply visible. Here they are heavily blurred by averaging. So neighborhood operations for gradient, and based on gradient, the edges are boundaries between objects. So the intensity gradient, you can see there is a horizontal boundary because there is a vertical gradient. There is a vertical boundary because there is a horizontal gradient, etc. So gradient-based operators can be used for highlighting the boundaries. So you can see the boundaries are looking much brighter compared to non-boundary pixels. So there are pure master's and doctoral level research-based operators which give you even better performance. So John Francis Canny was a student at MIT, and he developed a solid theory-based detector of the boundaries. So what he said was, in his theoretical requirement, low probability of missing a genuine boundary. Sometimes these image processing methods can miss genuine boundaries. They may pick up wrong pixels as boundaries. So he wants that. Also, false alarm means non-edge pixels reported as edge pixels. So that probability also should be low. Missing genuine edges, probability should be low. And you should get sharp single pixel edges, okay? And at the correct location where the boundary is, it should not be displaced. Okay, so there is some theory for it, how to go about it. Canny's original thesis, papers, tutorials on Canny edge detector, there is a lot of material available. Okay, but this is the input image. This is the Canny edge detector output. You can see how good the working of this is. Okay, all the small and large boundaries are picked up. If you are not interested in all the minor details, by choosing suitable parameters, you can reduce the number of edge pixels. So another set of parameters. So you can decide whether you want very, very strong major boundaries only, and you're not interested in, for example, you're interested only in land water boundary. You're not interested in the land part or the water part. You can do that also, okay, with the help of suitable parameters. Okay, so with the help of the gradient that we calculate, we can sharpen the images. So this is the input image, and this is after sharpening. So there are these spots which are actually buildings or houses. They're all picked up. The land water boundary also is now much crisper. Okay. Like in other signal processing operations, with satellite images also, Fourier transform and other transforms are quite actively used. You know the Fourier transform maybe in one dimension. So this is for 2 dimensions. So usually when you compute the Fourier transform magnitude for an image, it looks something like this. And how do you process images in the frequency domain? So with suitable pre-processing, you apply the Fourier transform on it, and on the Fourier transform magnitude and phase, you apply filters, and then you perform inverse Fourier transform, and with suitable pre-processing, you get a transformed image, filtered and transformed image. So like this is the input image, this is Fourier transform. So this is only the boundaries detected. The image is smoothed or blurred, and this is image sharpened. This is the input image. This is after sharpening. So you can see all these bubbles, etc. This is actually an electron microscope image of an IC. So you can see all these probably defects very, very clearly. Input, output. So sometimes you have rectangular objects. So how do you call it a rectangle? Digital images only have pixels. So you need to fit lines or circles, pass through these pixels, so that you now have equations. Suppose you want to extract a rectangle. So you need to first find the equations of the lines of the four sides. Then you have to find where these lines intersect. And on that basis, you can plot the rectangle, you can find its area, its perimeter, which are the corners, etc., etc. One of the ways to do it is through what's called a Hopf transform. So Hopf transform can be used to fit lines. Here we have only H pixels, boundary pixels, and after finding the equation of the line that passes through these pixels. Okay. So line detection, line fitting by Hopf transform is very, very well known and very frequently used. It's computationally also not very expensive. Because there are only two parameters to be determined for any line. Its slope and its intercept with the x-axis. It has, of course, a disadvantage that slope calculation becomes very difficult when the lines are vertical, because slope can go to infinity. In that case, an alternative polar coordinate representation of the line is used, like x cos theta plus y sin theta equal to rho, and theta and rho are determined for lines. So they are bounded, right? So there is no question of them going very large. Color transforms are used to get a hold on the colors. So whenever we see on the computer screen, any color you see is actually a combination of red, green, and blue. But if you want to explain what you are perceiving, you want to explain it in terms of green, yellow, purple, brown, orange, etc. So you have some colors and you have lighter, darker, brighter shades of them. Okay. So whatever is the dominant wavelength that is incident on our eye, we call it the hue. Whether it is lighter shade, so saturation will be less. It's a darker, brighter shade. The saturation of the color is high. So the saturation itself ranges between 0% and 100%. If you have white light, saturation is 0. If a color is diluted with white light, the saturation goes down from 100% to 90, 80, 70, 60, etc. So same hue, same saturation, but how much energy is available? So if you see a color object in bright light, the colors will be that much more clearly visible compared to in dull light. Okay, so all the three are important. How much energy is getting reflected from the color object and which we are receiving in our human visual system. So red, green, blue, alternate representation is the hue, saturation, and intensity. So you can tweak the hue and saturation for color enhancement, like an example here. So we have many other transforms. Fourier transform is one. The color transform is second. We also have something important called principal component transform. So if you're familiar with images, image processing, and image compression, we have something called Karhunen-Loew transform or the Hotelling transform. Okay, so based on the spatial autocorrelation of the image is compressed, or the amount of data required to store the image is reduced. Okay, and in satellite images, based on the correlation among the images acquired at nearby wavelengths, suitable transforms are applied so that you have reduction in the amount of data required to store a given data set. Excuse me, I'm getting some prayers. Can they mute, please?
Yeah. Sir, we'll take care, sir.
Yeah. So to explain what is meant by redundancy, if we look at two-dimensional data points, we can see that there is a lot of negative correlation between the values. So high B2, low B1, high B1, low B2. So by projecting the data onto some regression line, we can whose mic is on? It's too distracting. Okay. So essentially, the principal component transform, when applied to images, is used to reduce the correlation among the spectral channels, and that is done through the covariance matrix and eigenanalysis of the covariance matrix. So you can see an example So the image in blue band, green, red. So you can see a lot of similarity in the data. Can can the admin mute that particular?
Sir, sir,
Yeah.
I'm calling my actual admin. He is in somewhere, it seems. So. Please clear, sir. Otherwise, you are the co-host, sir. You are the co-host. You can also mute this.
Okay, let me see whose mic is open.
Sanjay Sonar. So mute చేశాడు. Now it is muted, sir. Now it is muted.
Okay, thank you. Because I was just not able to, it's too distracting. Okay, is the screen visible or do I need to re-share it again? Is my screen visible?
Yes, sir. Yes, sir.
Okay, fine. So if you see the kind of remote sensing images we get, the data in the blue wavelength, the green wavelength, the red wavelength, there is a lot of similarity. Okay. So if each one occupies, say, 100 megabytes, so you are carrying 300 megabytes of data, but there is a lot of, so in some wavelengths, the image may be different. In some wavelengths, it may be very similar. Okay. So dimensionality reduction can be carried out using the principal component transform. This is done in the spectral domain, in the wavelength, along the wavelength axis, while the regular image compression using KL transform, it exploits the correlation among spatially adjacent pixels. Here it is spatially, like adjacent wavelength bands in the electromagnetic spectrum. So by the principal component transform, we can reduce the data to a much smaller number. So for example, you can easily discard the principal components like this, which are too noisy. So this is practically useless. This is also not so useful. This one and this one carry much of the information in the original data. And this transform also is used for enhancing the colors in the display. So image interpreters will find this one a lot more useful compared to this. Some of the surface features, the differences in the surface features are much better visible after this particular operation. So the principal component transform decorrelates the data, apply your enhancement methods on that, and apply inverse transformation. This is what is done here. So this is one example. This is second example. You can see compared to this one you can see the differences in different parts of these paintings very clearly. And this is Aligarh town, and I think this is the city, some highway running through the city, plus some fields outside, etc., etc. So these are all like color enhancements through principal component transform. So you can see what kind of what kind of image processing methods are applied to images. Some of these are not very common to other images, say medical images or X-ray, ultrasound images, biometric images, etc. But another important application, if you are all familiar with Google Earth images, the satellites that supply data to Google company, they acquire very high resolution black and white photographs, black and white images, and relatively coarser resolution color images. Okay. So this is high resolution but black and white, coarser resolution but color. So these two are merged through the color transform and the principal component transform I mentioned. So you get both advantages, color as well as high spatial resolution. So this is called data fusion. So this is another example. This is through the color transform. This first one was the principal component transform. This is through the color transform. So actually Google uses this kind of data to give us the nice high resolution color pictures through the Google Earth platform. Okay. So different wavelength combinations have given rise to different kinds of color images. This is called a true color image. Here there is, I think, dates or some plantations. They are seen in the natural green colors. Here, instead of the blue, infrared is used. So vegetation very strongly reflects in infrared, and infrared data displayed in red color. Wherever vegetation is present, you will see it in red color. That's why such images are called false color composites. Google doesn't bother to give you false color composites because they have to buy infrared data, since they are giving you free data, they use only the true color images like this. So another kind of satellite image processing is to highlight specific areas. So if an image covers desert areas, there is an index specifically to highlight desert areas, snow-covered mountains. So there is a separate index to highlight the snow-covered areas. For water, you have a water index. Vegetation, you have a vegetation index. Essentially, the property exploited is everything has high absorption in one wavelength, high reflectance in another wavelength. By combining these two, taking ratios or normalized ratios, you can highlight those features. Okay. So here, for example, the bright areas are all where vegetation is present. So here you have woodlands, agricultural areas, you have golf courses, that is green grass covered areas, all kinds. So they're all in different bright shades. Okay, so these indices, so there can be, one can compute a water index and show the water, whereas all these will be subdued. You will see more details of the water. Okay. So from one kind of images, you can move to another kind of images through image processing. Okay. So from absolute raw data to more useful, still image data only, it's not information as such. If the human expert is looking at those images, the human expert finds the processed images more convenient, more comfortable to identify whatever is of interest. Okay. But you don't have that many experts in this world. The requirements are huge. But you don't have certainly that many experts, human experts, who can work 24 hours a day interpreting images. There will be fatigue, there will be mood change, there will be inadequate expertise in some people. There will be unfamiliarity with one kind of images, more familiarity with another kind of images. Therefore, if machine learning algorithms can suitably be developed for specific applications, then they will be, the computers can work, if required, 24 hours, 7 days a week, processing data in batch mode. Okay. From satellites around the world, if you see, every day about 1 petabyte of data is downloaded to ground stations. 1 petabyte, that is 1000 terabytes. That is 1,000,000 gigabytes. Okay, so that much data is coming every day. So depending entirely on humans is impossible. Okay, so suitably trained computer classifiers can be deployed for information extraction. Of course, it doesn't completely remove the human expert from the picture, because how much of the human expertise can be computerized is still a question, and there's a lot that a human expert can do which is difficult to code. The expertise, the intuition, the guesswork, all this is not possible to encode. So when we talk of machine learning, so the learning through a computer program extracts useful knowledge from the data. And whether this process is suitably stable and accurate, for that, what we do is we use some data for the learning purpose. Learning, that is, the computer has to learn what is the relation between the input data and the desired knowledge. So that is the learning phase. So some sample example data is provided to the learning program. Now, whether the learning is satisfactory or not, that is to be tested, validated. So for that, now the learning phase is removed, and just that some new data is fed to the program, and the results will be looked at, whether the program has given the desired results or not. Okay, so that is a generalization phase. So a child, for example, looks at some toys, a few toys maybe, which are brought home by the parents, and then when the child sees a similar toy at his friend's place, the child will immediately recognize it. The child would not have seen it before, but the child has learned the characteristics, the interesting features of the class of toys from the examples provided at home. Okay, so that is a generalization, correctly identifying what was not seen before with the help of the understanding gained through examples. So these examples in image classification and analysis literature, they are called the training samples or labeled samples. Okay, so when we see things, we look at its color, it may be the surface texture, the shape, okay. So many things which are like our descriptors with which we identify objects. So in machine learning terminology, they are called features, okay. So the wavelengths in which the data is collected, they are features. And then maybe you extract some boundaries or edges. You may extract something called texture. Okay, I've not gone into the details of texture analysis, but texture is one thing which is very, very powerful feature. So now if there are samples available whose labels are also known, okay, as far as satellite imaging are concerned, so these are water pixels, these are forest pixels, these are agriculture pixels, etc. If that labeling is given beforehand, then we call it a supervised classification approach. If such labeled samples are not available, we call it unsupervised classification. This is as such domain independent. Okay, not only satellite classification people, others also may use this approach, supervised versus unsupervised approach. Okay, so how do we relate the data to the classes? Okay, with the help of the examples, we can come up with a statistical distribution of the data values in each class. Okay, so this is generative modeling. So we generate this distribution, probability distribution, given the class. Okay, now we use this for discriminative modeling. So we want to discriminate, given the data, we want to discriminate between different classes and see which class may be having the highest probability given the class, which class is most likely. Okay. So when we say we provide examples to the classifier, what does it learn? Typically, these are some of the things it learns. For each class, it will learn the mean vector. So if my data is available, supplied in multiple dimensions, then average of each dimension in each band will lead to a vector of the mean vector. So within each wavelength band, you have variance. Between bands, you have covariance. So you have a matrix of it. What are the minimum, maximum observed levels within each wavelength band? How much is it in red, green, blue, infrared, etc.? You can find these things. How are these samples actually supplied? As far as satellite image processing is concerned, the images are displayed. Suppose an expert is sure that this part is seawater. Okay, this actually is creek, a sea creek. So this is water. That is, all the pixels under this white rectangle are to be treated as water pixels. Okay, this is like a using a graphics tool. This is drawn on top of the image. Here you have slum houses or slum hutments. Here you have buildings, mangrove vegetation. You have this, usually water is collected for preparing salt. Okay. So this is one such area. And then you have patches of roads. Okay. And you can have many other kinds of these things. For example, this is one kind of building, you have another kind of building. This is a central jail. You have different kinds of buildings here. Okay. So we can define as many classes as we like. This is seawater, dark, swimming pool. Obviously, you know, the depth of the pool is something like 3 feet to 15 feet. So a lot of reflectance from the bottom where blue tiles are there. So you can distinguish between this water and this water. Okay, so an example of the classifier which classifies the pixels in the data is like this. So this is the mean vector for class I, ith class. This is its covariance matrix inverted. This is the absolute probability of finding that class in the image. This comes from historical information. By doing all these calculations, you can say what is the likelihood of ith class, I equal to 1, class 1, I equal to 2, class 2, etc. And with the help of this, we can find out, given the data vector x, what is the most likely class to which it would belong. So an image like this, after classification, it is color coded. Each color is represented in one color. So instead of the pixels, you have now the class labels. So if you want, you can estimate what is the area of water body in this image. What's the area of forest in this? What's the area of different kind of cropland? What is the acreage of the croplands? So this kind of, you have a town here, Varanasi town. What's the area of that township? So you can do these quantitative calculations, count how many pixels in a class, what is the area on the ground per pixel in square meters, multiply with the number of pixels, that gives you the area of coverage of that class. Now, suppose this is collected for one date. Collect the image for another date, or repeat the same classification, and then you can match whether the classes remain same or there is a transition from one class to another. Usually in urban areas, what happens? Open spaces in one date, and the next date, open spaces get converted to buildings. So you can detect the changes. Even water bodies are filled up and they are used for construction, leading to disastrous flooding, as it happened in Chennai, Bangalore, Hyderabad, and so many cities. And there are so many kinds of classifiers. So if an unknown sample is given, find the nearest labeled sample and assign this to the same class. This is called the nearest neighbor classifier. Now you can also have, how are the classes separated? Okay. So all you are given is the labeled samples. Now you have to find out how to separate them. In the previous case, you have ready-made formulae available with which you are classifying the data. But here, you don't know how to draw the boundary between classes, okay, in the features, not on the ground, but in the features. So that is, I have a set of values for water, another set of values for vegetation, etc. in multiple dimensions. So based on the values, how do I say that this set of values belongs to this class, this set of values? I have only limited number of samples. I don't know. I don't have all possible values for all possible classes. So then you have to use learning algorithms, machine learning algorithms for this purpose. First, define the zones in which the values of different classes lie and accordingly carry out the classification. Okay, you have a discriminant function. Okay, so if you are able to draw in 2 dimensions, you can draw a line separating one class to the left of the line, another class to the right. 3 dimensions, you put a plane, and in higher dimensions, you put a hyperplane, separating data into different classes. So when you say you are doing this, all you need to know is what are these parameters of the line or plane or hyperplane, etc. So you are given some samples X, and you are also given which classes they belong to. So based on that, you need to define these lines or planes or hyperplanes. So if you say there is a hyperplane, you have to find its parameters. So one of the beautiful such classifiers is the support vector machine. Okay, let us quickly go through how a support vector machine works, taking example from 2 classes. Suppose I have some values that are typically encountered in class 1 and in class 2. These are the values typically encountered. For convenience, I have drawn it in 2 dimensions. So I can separate these 2 with a line. Okay, to the right of the line, you have class 1, to the left, you have class 2. But suppose I drew this line, this is also valid. I drew this line, this is also valid. All of these are valid separators. So there are some classifiers that give you some way of separating these 2. There is nothing like an optimal class separator. Okay. So if you remember the fact that these are samples given for class 1 and class 2, then there can be other samples whose values may come slightly to this side, or they may go slightly to this side, in which case they go into the wrong classes. So this particular boundary is not a good one because it doesn't allow much scope or margin for the samples to vary while staying in the same class. So the critical values are those which are close to the separating line or surface that we put. The far off ones don't matter. The ones which are close, these are the ones that can go wrong. Right? So compared to this, what about this? Now, all I did was change the slope of this line. And now I have a different line intersecting the x-axis at a different location. So this line has a different slope, different intercept compared to this. Here the slope is left, intercept is closer to the origin. But see the interesting thing here. There is more margin for samples of this class to vary and still stay in the right class. They're not going over to the other class immediately. Same with this class. So this is a better separating boundary compared to this one. But so how do you arrive at this? So this is the working of the support vector machine classifier. It's one of the very heavily used classifiers. So what you need to do is, if I get some slope and intercept, I can draw the corresponding line, and given that line, I'll know how much margin is there. Okay. So if I'm given some line, I can find out how much margin is there for the nearest samples, okay, from the separating boundary. So can I find the slope and intercept in such a way that I can maximize this margin? So I can make it an optimization problem. Okay, so maximize the margin. Okay, that is, find the slope and intercept of this such that the margin is maximized. And what are there any constraints? Whenever you say optimization, you have unconstrained or constrained optimization. What are the constraints here? The constraints here are that the samples which are to the right of the line, they should produce, let us say, a positive output, and that is with respect to it. Okay. And on the other side, these should produce values of a different sign. Okay. So like, for example, in the xy plane, to the left of y-axis, you have negative x. To the right, you have positive x, right? Same way, the points here to the right of this line should have positive values, and to the left, they should have negative values. Or you substitute the data vector in the equation for the line or surface, whatever, hyperplane. So when you substitute the data vector in the equation for this, you should get, let us say, negative value for the samples of this class and positive values for this class. Okay. So those are the constraints. All points on this side should have positive values when they are substituted in the equation for this line. All of these should produce negative values. Okay, so you have the constraints and you have the optimization problem. Give me the parameters of the line or the hyperplane that gives me maximum margin from these samples which are on the opposite classes but closest, which are closest. The faraway ones don't matter. They will anyway be on the right side. The ones which can go wrong are the closest ones. So these closest ones are called the support vectors. These are all vectors, and mathematically support means it defines the validity of a function. Okay. So this separating boundary is like a function. Okay. So for that function, the nearest samples provide the support. Support vector machine is a classifier. That is how the terminology support vector machine comes. Okay. So why you consider only the support vectors? You have some justification. So with coordinate geometry, we can find the equation of a point from the line or the surface or the hyperplane, and the margin, given this, the margin is the distance of the nearest data vectors. And how do you maximize the margin? Okay. So given the parameters of the line, that is for 2 dimensions, it will be just slope and intercept. Given that, which are the nearest ones, which have the nearest distance to that, they give you the margin. And now we are trying to maximize by finding the optimal values of this W and B. So that is the optimization problem. And this is the constraint. Okay. So the positive and negative values that we expect. So they are compactly written. Okay. So if the sample belongs to the right, this Y value will be right. And if the sample comes from the left, Y value will be negative. And so in all cases, this product will be positive. Anyway, this is for convenience and implementation, derivation of the solution, that we are not worried. Okay, so this is how the support vector machine works. Here are some nice classification examples. I've given you the reference. This is open access. You can always download the paper and read it. So if you learn the theory, if you read up on SP support vector machines, you know sometimes the data may have to be pre-processed through nonlinear transformations. Okay. So these are different examples of it. We have also neural networks. Neural networks are like this. Neural networks like this, they give you some boundaries without concerning themselves with the margin. Okay. But neural networks are also fairly powerful, and they have their own advantages, particularly with the deep learning that has come about. The neural networks are very powerful tools. So neural networks work on the basis of estimating the error between the desired and computed result and minimize the difference between those two. Okay, so whatever is the error or the difference between the computed and the desired outputs, that is propagated back, and the network is reconfigured iteratively till such time you get nearly correct output for all the samples, training samples that you provide. And once the training is complete, it is tested for generalization. So whatever samples are used in training are not repeated for testing. And if the test samples are also correctly classified, then you will get the network which can be used in applications. Very similar, you know. So you teach your students, you solve some problems, and then that is the training phase. New problems are given in the exams, that is the testing phase. So students who solve the problems in the exam score good marks, they'll finally get their degrees. They'll be qualified for their engineering jobs. So some examples for classification using neural nets. Okay, so here I had only a black and white image, so which is very difficult to classify. So I derived some additional things called textures, and based on that, I did a classification with neural networks. Okay. So how are we doing for time? 7 to 9. So I have 14 minutes. So I'll briefly introduce deep learning. Typically, when you say deep learning, let us think of our own way of dealing with complex problems. So we have different kind of knowledge stored, and we connect so many different things that we have knowledge of, okay, and we may use all of it in different ways, connecting all those things to come up with a solution to a very complex problem. Okay, an example can be, suppose there is a difficult situation that a doctor sees in a patient. Okay, so it's not easily known what the problem is. So the doctor may do different types of investigations and then combine maybe the kind of say blood chemistry values, the kind of lipid, cholesterol, triglycerides, maybe urine analysis with X-rays, MRIs. So using what information that is revealed by different things, they will all be like a lot of features for a classification problem. Patient is healthy or not healthy, or patient is healthy, or patient has disease X, disease Y, disease Z. So in trivial cases, for example, somebody has fever, so it may be, say, viral fever, or it can be more complicated, more investigation, whether it is typhoid, malaria, or something else, or the patient has fever as well as maybe some cough and other things. So maybe more dangerous things like tuberculosis, pneumonia. So by looking at different kinds of knowledge from different kinds of investigations, more and more complex problems are solved. So that is how the deep learning has, it's like, a neural network with a very large number of layers which solve the problem in a phased manner. Finally, when you come to the last stage, you may have the solution, but that requires, so for computational deep learning, you may require supercomputer level resources. Okay. So some amount of computational simplifications are done through what are called convolutional neural networks. So the deep learning problems, the number of unknowns are what are called hyperparameters in deep learning literature. They are reduced by using convolutions, because particularly in image analysis, the information about a pixel lies in nearby pixels. Okay, so whenever we are trying to extract useful features from images, you don't need to use all pixels of the entire image. Instead, you can use the patterns that are extractable from pixels and their nearby neighbors. So we have these convolution operations performed on small neighborhoods. So we can get gradients, okay, intensity gradients. Then you can also smooth the images by suppressing noise present, and then you can get texture information. So like that, you can use multiple operations instead of using all pixels in a huge network. We extract useful features through these convolution operations, and with the help of that, okay, so instead of using all the elements, we use nearby elements. So we have convolutional neural networks. The convolutions, they only get you the features, and then at the end you have your neural network. Okay, neural network, then it performs whatever classification is required, and it gives you the desired result. Okay, so a number of these convolutional filters are used, and there is also more calculations involved in between. A data reduction happens through what is called a pooling stage. So maybe there will be dedicated lectures on this, so I'm not talking about all the details. So all these convolutional stages, at the end, they give you the feature vectors. And after they are generated, you have a regular neural network. But this is a small network. This is not a huge network, okay, which would otherwise have been required. Okay. So you have different kinds of applications of the convolutional neural nets. I'll show you some examples with high dimensional data. Okay, for example, suppose I have a low resolution image. Okay, so this is simulation. So original data will be sharper like this. Suppose I have a coarse resolution version. So can I enhance its resolution, or what is called a super resolution approach for improving the resolution of images that are acquired in low resolution mode? So you can use the convolutional neural networks for super resolution applications. So it may come close to this. It can come closer to this, but this is only an example. Second example, so this is more visible to the eye as to how good the result is. Original simulated low resolution version and the super resolution output. So you can see this is a much blurred version of this, whereas this is much closer to the original. So whenever we deal with the images, usually pixels are looked at like atoms. You know, you can't go below that. Atoms are considered the basic units, but with convolutional neural nets, you can also improve your classification at a subpixel level. Particularly when you have coarse resolution imagery, suppose a pixel on the ground covers 1,000 square meters. In 1000 square meters, you can have a couple of buildings, you have some open space, and maybe a tree or two. So many things. So what you observe at that pixel is a mixture of whatever is reflected from all these different things. So can I look into the pixel and say, look, this part of the pixel is actually vegetation, this part is buildings, this part is open space? Can I do that? Interestingly, convolutional neural networks have been used for such applications also, which is called subpixel mapping or subpixel classification. If the original image is classified, it will come like this. The coarser resolution version of this, so it is classified. Now these two are pretty close. So you can ask a question, if this is full resolution, the coarse resolution one is also of the same size. If I actually show it as a coarse resolution image, it will occupy a very small area on the slide. You will hardly see anything inside. So this is enlarged just for the purpose of viewing. Otherwise, this one is about 1/3 the number of rows of this and 1/3 the number of columns. That will be very small. But subpixel classification has given you nearly similar results. Third example. So convolutional neural nets are also being attempted. This is still an area of research still going on. Suppose I have 3 channels, blue, green, and red. Between blue and green, you have about 100 nanometers transition, 400 nanometers to 500. So in between, can I get the intermediate images? So if these are 3 filters with 100 nanometers separation, can I get, for example, 400 to 420, 420 to 440, 440 to 60, up to 500, then 500 to 520, 520 to 540. Can I get the wavelength band images at intermediate bandwidths, intermediate band values? That is, here the images are 100, the bandwidth of the images is 100 nanometers, very coarse spectral resolution. Can I improve the spectral resolution? So that is spectral super resolution. It is still going on. And then convolutional neural nets are also used for object detection. So here all the planes are picked up by what is called region RCNN, region-based convolutional neural net. Okay, there is a lot more material in my slides, which I'll share with you. But I think I'll stop here. We are almost close to 9 o'clock. It's already 9 o'clock. So I stop here. So if Professor Narasimha Garu permits, I can take a few questions from the audience.
Sir, yeah,
Yep.
I request participants can ask the questions. Now it is an interaction session. So whatever the queries you are having, so please proceed. Please unmute your mic and you can ask any questions.
Yeah, dear participants, please interact with the speaker.
So shall I stop sharing my screen so that I can see everybody?
Yeah.
Okay, a lot of people. Dinner time, but they're all there.
Sir. Already it cost 65. It cost 65, sir. Now few of them have left.
Yeah, that's a very decent number, actually.
Yes, sir.
Okay, so I had introduced this particular domain of satellite image processing. I gave you a few examples, different types of satellite images, how they are practically used, how they are practically dealt with different machine learning methods. So I'm hoping deep learning, there will be dedicated lectures. So I did not go very deep into it. Otherwise, you can have a 2-hour session entirely on convolutional neural nets. You can have another 2-hour session entirely on these region CNNs, etc. Okay, so any questions, or people are too hungry to ask questions?
Yeah, dear participants, please interact with the Krishna Mohan sir. So if you have any queries. Hope the participants are, as you said,
That they're probably too hungry.
But unfortunately, this AICTE also has given this time, sir, 7 to 9:30.
Okay.
And under impression that they have completed their classwork and all, evening they would be free.
Yeah. This is very rare that we have lectures from 7 to 9.
Yes. Sir, in the chat box, you can see, sir, most of the people are expressing their views. It is a nice session. Most of the people are expressing. Yeah, anyway, sir, I thank you, sir, for your sparing valuable time, though you are busy, even in the evening times. As and when I ask you to give a session, you accepted. We are very much thankful and grateful to you, sir.
Yeah.
Hope the participants have got several insights on the satellite image processing and the trends, and particularly you also covered deep learning and the neural networks, SVM, all other techniques also. So definitely this session will be useful, will be benefited, and all the participants will get benefited. So with these few words, I once again thank you, sir. Okay.
Yeah.
With this, we can conclude, sir.
Sure. So I'll email you the PDF version of the presentation, which you can share with the participants.
Sure, sir. Sure, sir. Sure, sir.
Yeah.
Thank you, sir. Thank you very much.
Send me your Gmail address because the file is pretty big.
Sir.
So you can WhatsApp me your Gmail address so that if it's not possible to send it by regular email, I'll send it through Google Drive.
Okay, fine, sir. That is narsimulcv@gmail.com, sir. Earlier I sent you mail.
Okay, yeah. If you have been regularly sending mails through your Gmail account, then I'll find it.
Fine, sir.
But if you're sending through your college link, then it may not go through. But
another mail is the regular mail.
Okay, so just WhatsApp me your Gmail address. I'll send it to you.
Definitely, sir. Definitely. So
okay.
I can also share my participants.
Sure. Yeah, you can give my email address to the participants also if they want to correspond with me for anything. I can correspond with my IIT Bombay email address.
Sure, sir. Sure, sir. I will share.
Okay, everyone. So all the best for the rest of the course. Thank you very much for staying online.
Yeah, thank you all. So
okay.
Thank you, sir.
Yeah, I request all the participants. I request all the participants join tomorrow also in the same timing. So Dr. C. Raghavendra Rao from University of Hyderabad. Okay, we'll address you tomorrow.
Thank you, sir. Thank you so much for the session.
Thank
sir.
you. Thank you all for being there. Okay, bye. Good night.
Thank you, sir.